Wonderful. Okay, so wait just a second. I'm sorry. That's embarrassing. Okay, never mind. Okay, so hello everybody. Today I'm going to be talking more about BPS states like I did last time. Just to quickly summarize, like, where we're at in the semester, what we've done. I mean, I see there's a person here who isn't usually here, but basically we're looking at supersymmetric field theories and basically the sort of structures you can get from them, in particular these stuff called integrable structures, which we haven't actually talked very much about, but I hope to change that today. So the sort of founding, work in this theory is this work by Seiberg and Witten, which just sort of started everything, right? So this is in 1994, and they, gave this first example of analyzing the Coulomb branch geometry, and they gave this explicit solution, and they used BPS states and all of those things, and these are all very big topics now. So I'm going to be basically building off of that and talking more about the Coulomb branch geometry. So let me review a bit about what I talked about last time, which was basically a whole dive into the Seiberg-Witten solution in some detail. And this is a solution to the question of what is the low energy effective field theory for n equal to super Yang-Mills theory for gauge group SU2. It's kind of a mouthful, but basically you have this very, very simple, very easy to describe Lagrangian, very easy to describe field theory. The question is what happens when you step really far back and sort of see like what it does, what are the emergent dynamics? And then this is classified by this effective field theory they found. And this is done using these techniques of both BPS states and this Coulomb branch geometry. So the first step is what possible field theories could it even go to? So these are actually parameterized. There's a whole family of them, basically representing different directions you can point in 4D space, 3D space. So there's a whole moduli space of vacua, which we call the U-plane or the Coulomb branch. And the idea is at these places, in the large energy limit, it's not SU2 anymore. It reduces down to U1. So we have an effective field theory where now suddenly it's a simpler gauge group, and now it's like electromagnetism. So that's where the Coulomb and Coulomb branch comes in. Right. So the sort of structure, the main structure that they used on this state was this charge lattice. So at every point on the moduli space, we have a lattice. This is going to be a lattice because of some cool stuff with electric magnetic duality. And we know this lattice exists as we go off to infinity, because then it's very weak and it falls into semi-classical approximation. And we can actually look at what the BPS states are, what the states are. And they correspond to monopoles with a given charge. And those different charges are given in a lattice, and that is what happens at infinity. And as we deform out from infinity to the more quantum stuff, these lattices deform along with it. And the structure of the deformation is what they use to get the theory. So this lattice has the structure of, well, it's parameterized by these two functions. And we're saying that it varies holomorphically in these functions. So it's a holomorphically varying lattice. And we actually have a nice symplectic pairing, which is from Dirac, the quantization condition gives you a natural way to a natural symplectic pairing on this map. And the really cool thing is that we can express these two coordinates of the lattice are not varying arbitrarily. They're actually related to each other with what's called a free potential. So this is a holomorphic function on the lattice. This is the thing that immediately gives you the low energy Lagrangian. And basically, we're saying that the two lattice coordinates are dual to each other under this prepotential. This dual coordinate AD is the derivative of the prepotential with respect to A. So this charge lattice, it's parameterized by two different very nice coordinate systems on our base. So at the base, most of the places, it's just a nice happy U1 theory, and you have this nice charge lattice, and it deforms, and maybe as we get closer to a point, maybe it becomes singular. Basically, that happens when the lattice degenerates. It all points in one direction, and then you have to do more complicated stuff. So that is the gist of the Coulomb branch geometry, and that is what they use to get their theory. But let's look a little bit closer at this, at these structures. Let's try to generalize them and abstract them beyond just their physical interpretations. So let's see what we have. We have some Coulomb branch. Let's just call it a manifold. And we're going to have some place where the lattices break down. That's going to be a codimension 1 singular locus.
Is this M assumed to be a complex manifold? I mean, the case you had, it was a one-dimensional complex manifold.
Yeah, usually it's scalar. It's always scalar.
Okay.
I don't know if I need that in.
Yeah. Okay.
It's
and
scalar.
So codimension 1 means codimension 1.
Complex codimension.
Complex codimension.
So this is what the picture usually looks like. Oh,
right. Okay.
This is sort of the generic picture. Is that there's like a hole. There's holes in it, and it's all connected, but you can still go around things. Oh, that's concerning. Okay. Well, my pencil just ran out of charge, so I'm going to have to use my words. Right. So we have a Coulomb branch. We have a Kähler manifold, and we have a singular locus where stuff breaks down. But outside of that, everything's nice. Everything gives you this nice low energy effective field theory where it's just a U1. And we get a nice charge lattice on these points, which for us is just going to be sitting inside a vector bundle, a rank 2 and vector bundle. And in this case, what I'm talking about is the real rank, not the complex rank. So I'm being a little bit confusing about that. But this vector bundle is going to have a whole pile of structures on top of it. In particular, first we have the symplectic pairing over here. And that means we can think of this vector bundle as having a symplectic structure too. And then the analog of the charge lattice is just some lattice, some sublattice, some real sublattice of this vector bundle. Pointwise, you give it the sublattice and you have it very continuously. And then you give it a flat connection. So it's going to be a flat vector bundle. And this connection is going to, we demand that it preserves the charge lattice. So we have a bunch of flat sections moving around inside of our bigger vector space. So what we can think of this as is, the flat connection it's like a structure group of symplectic transforms, because we're going to be preserving the symplectic structure, but because we're also preserving the charge lattice, we're reducing that from any symplectic manifold. No, it has to be integer valued symplectic matrices. So that's what we're working with. And so far we didn't do anything too crazy, but the real juice on it comes from this pre-potential, and how it interfaces into this is through the central charge. So this is going to be just a function that takes your lattice and sends it to C, right? And it's useful because it actually gives us these coordinates up here. Like we're defining these coordinates to be essentially the value of Z. Let's see. Yeah, so Z is just going to be okay. Z is just going to be the sum of these electric and magnetic charges and these coupling constants attached to them. So in particular, notice that this is already, I should have mentioned this is all in the rank 1 case. So your charge lattice is literally a lattice, everything's 2D, but down here, I'm doing a more general theory, right? So these coordinates, as we set up here, they're going to satisfy this sort of this duality relationship. But now every pair, there's going to be n pairs of coordinates, and they're going to all satisfy that. So all of this together turns into essentially a special Kähler metric, a special Kähler structure. And that's where we're going to get all of the nice special stuff on our manifold, the special Coulomb branch geometry properties. So we can define it by taking the derivatives of these two coordinates with respect to each other. Now, what I want to do today is
hold on just for a second. That metric, the Kähler metric, ought to be Hermitian. So one of those DZs should be a Z bar.
That's a good point.
And so that also probably means that, so either the derivative is the anti-holomorphic derivative or the quantity whose derivative you're calculating is anti-holomorphic. So if you chose that Z bar on the ZJ, then the derivative is by the conjugate of A0J or whatever that is in the denominator, so to speak, of the derivative.
Oh, I'm sorry, that's a D representing duality.
Oh, okay, sorry, D, yeah. So that should be then the conjugate function.
Okay, so you're suggesting it looks like this?
Yeah.
Okay. Yeah, I don't think that'll mess anything up later. I just wanted to write down the metric here so we could see what it looks like. So the perspective that I wanted to take, yeah, thank you, by the way. The perspective that I want to take is to think of the structure through the lens of variations of Hodge structure. So these are these things where if you're not familiar with them, they're kind of hard to stomach, but if you've done complex geometry stuff, they kind of come up all the time. So, oops, maybe people are already familiar with it, but it doesn't hurt to review. So the idea is, we're going to start with just the idea of a cohomology bundle. This is our prototypical example of a variation of Hodge structure, where we have a manifold that's varying as a function of a point on the base. So it's a family of complex manifolds, and we can just take at every point, we can take its cohomology. So that's a vector space, and we get a nice vector bundle. And it has extra structure too. It has a integer lattice by taking the integer cohomology. It has a nice flat connection, the Gauss-Manning connection, which you can think of as just taking your homology or cohomology class in this fiber and just moving it over to this other fiber. And so it gives you a way to move move your sections from one place to another. And it has a Hodge structure. So this is, in complex geometry, we can sort of split up these differential forms into their holomorphic and anti-holomorphic parts, which we can arrange into a nice filtration. I'm not going to go into too much detail in this because we're going to only use very simple versions of these. And the last condition these have is this property of transversality, which says that this flat connection, well, it does preserve, this whole cohomology. It preserves the lattice. It does not preserve this filtration. It does not preserve the Hodge structure. Instead, it kind of, but it only breaks the Hodge structure in like predictable ways. So it just moves everything down one layer under filtration. So yeah. And the idea is a variation of Hodge structure is something which does all of this stuff, but it doesn't have to be cohomology. Like it's just the abstract vector bundle that has all of these nice properties. It has a flat connection. It has a lattice preserved by that connection. It has filtrations, which are holomorphic subbundles, and it has this transversality property.
And that transversality property also includes that on the associated gradient, you get an isomorphism, right?
Yes, that does not follow immediately. Yeah, I think so.
Okay.
So that gives you like this isomorphism from P comma Q to something like that.
Although the connection is flat, it presumably has monodromy.
Yeah, it does have monodromy. That's it. Because right now, I'm kind of looking at this in this trivial case, but in reality, this is only going to be a family of manifolds outside of some singular locus on the base. And where this singular locus hits, if we go around that, we're going to get monodromy of the flat connection. And that's going to have all the interesting stuff that happens in Hodge structures. Yeah, thank you. So our Coulomb branch geometry, we can think of as a special type of a very simple type of these variations of Hodge structures. It's going to be weight 1 and polarized. So to translate that a little bit, a weight 1 variation of Hodge structure means we just have some complex vector bundle, and we specify a holomorphic subbundle. So it's weight 1, so we don't have to deal with all of these flags or anything. It's just a single subbundle of a vector bundle. We're also going to make it an integer Hodge structure by specifying a lattice. And also, we don't have to worry about Griffith's transversality because it's automatically satisfied because the only place that our smaller filtration can go, our subbundle can go, is to the whole thing, which is what it needs to do. So essentially, we don't have to worry about this. And then we're also going to give it a polarization, which is essentially a symplectic pairing on the integer lattice, such that it plays nice with the Hodge structures. And in this case, what that means is it's going to be 0 when restricted to this subbundle. And we can also think of the opposite subbundle as the quotient of these two guys. So we can think of this as just a direct sum of two Hodge structures, two cohomology spaces, not cohomology spaces, two vector bundles. Sorry. Yeah, so basically it's going to give you a non-degenerate pairing if we do a sort of skew Hermitian thing and we take the inner product, but we conjugate it. So conjugation swaps this 1, 0 with 0, 1. And that's going to give you a non-degenerate form. So that's called a polarization. And in particular, we can look at all of this stuff and think that, you know what, that looks kind of familiar. I just saw it up here. And we can build a little bit of a dictionary, right? So this, the charge lattice, the charge lattice is the integer lattice part. That's going to be our charge lattice. And the full vector bundle, that's going to be the complexification of the lattice. So in particular, if lattice is isomorphic to z to the g, then this is going to be c to the g. Let's do 2g. Right, so it's a complex vector space, but that's not the vector space we see. The vector space we see is the sort of what you get when you divide out the holomorphic bundle from this full bundle. And that gives you this real vector space here. That's what contains the charge lattice in this picture up here, right? So this is a real vector space, but we're thinking of it as a half-dimensional subvector space of a complex vector space. And we also have this nice symplectic pairing, which gives us a polarization. And we care about these weight 1 Hodge structures, not only because they are what show up in these charge lattices, but because they parameterize abelian varieties, right? We have a direct comparison from these Hodge structures to just complex tori that are also projective. And it's pretty simple. You just kind of take this vector space here and mod out by the lattice, right? So we can instead think about that in terms, it's kind of expanded out in terms of a whole space. We have the whole cohomology, and we have the holomorphic parts plus the integer parts. So this is something that should be pretty familiar from if you've done Riemann surface stuff, because this is how you construct a Jacobian. Right, so this gives you a complex torus because you are literally just taking a vector space model lattice, but where you get the extra variety structure is with this polarization. Because in this interpretation, the polarization actually gives you a polarization on this complex torus, which you can think of in a lot of ways, but one way to think of it is as a integer valued second cohomology class that corresponds to a line bundle that's ample, and that gives you a way to projectivize this torus and map it into projective space. And once you do that, it becomes a variety. So polarized abelian varieties are stuff people like. And this gives us this, these correspondences. If we instead, I just described this for a single Hodge structure, if we do a whole family of Hogg structures, then, a variation of Hogg structures, then instead we're going to get a whole family of varieties, right? So I kind of hinted at this, that this torus you get here. Oh, I should probably stop to make sure. Are there any questions? Do a little bit of a. Okay. So I kind of hinted here that this torus, you can think of it as, I gave the example of a Jacobian of a curve, right? And basically that is a sort of geometric realization of these variations of Hogg structure, actually realizing them as true, Hogg structures coming from families of manifolds. And in particular, what we can do is we can realize these tori as the Jacobians of curves. That's called the Seiberg-Witten curves. So we talked about these a bunch last time, but yeah, as I was saying, your vector space is isomorphic to the real cohomology, and we mod out by the first homology group, the integer value cohomology, and that gives you your Jacobian. And your symplectic pairing, you get that directly from your Seiberg-Witten curve. That's just from the intersection pairing of curves the intersection pairing of cycles on your curve, right? So in the original Seiberg-Witten case, we had the gauge group of SU2, which ended up giving a one-dimensional complex manifold, and it gave a two-dimensional space. We needed to realize a two-dimensional variation of Hogg structure as, geometrically, which tells you automatically that this has to be a genus 1 curve. And in particular, it's an elliptic curve. And elliptic curves are nice because you can just write down their equation. In general, we're not going to have it so easy. Let's take our gauge group to be, I don't know, SUn plus 1. And in that case, if you do the whole dance of figuring out what the low energy, what the moduli of vacua is and all of that stuff, we're going to get that it's n-dimensional complex space. And we're going to get that the charge lattice lives inside of a 2n-dimensional real vector space, which means that to realize that as the first cohomology of a manifold of a surface, that surface has to be genus n. And usually, not always, but in a lot of nice cases, the surface is actually going to be hyperelliptic, which is like an elliptic curve, except there's more x's. It's realized as, this formula of y squared equals some polynomial of x. So let's take a little bit of time to describe this in a more invariant and geometric way. So we define using this polynomial in x here, that's going to give us a quadratic differential valued in the the square of the canonical bundle. It's going to give us a quadratic differential on the Riemann sphere on P1. And the curve we get, the hyperelliptic curve, is determined from this quadratic differential by the so-called spectral curve, right? So the spectral curve, so for example, in SU3, our curve is going to have, our quadratic differential, just looking at this polynomial, it's going to have a double pole at infinity, and it's going to have 5 roots on the inside. And the idea is we can take essentially the square root of our quadratic differential at each point, but the thing is there's 2 square roots, so we get 2 levels. So more formally, it's going to be the solution to this equation, which is going to cut out a subvariety, a subspace, a subcurve inside the cotangent bundle of your sphere. So we can imagine we had a sphere here before that had a quadratic differential on it, and we're at each point, we're looking at its positive and negative square roots, and we're tracing those out, and we get a 2-sheeted cover of the sphere. And we can relate the genus of the curve with the number of vantage points and stuff like that. So for those of you familiar with Higgs bundle stuff, quadratic differentials are quadratic differentials are very naturally appear as rank 2 SL2 valued Higgs bundles. And that gives you the name spectral curve because you're thinking about this as a matrix and you're literally graphing the spectrum of the matrix. It's a curve from a spectrum. Yeah, so that gives us a realization of the vector space and the integer lattice inside and the polarization. But there was one more thing, this sort of more special part that was related to the central charge. So the central charge is just some character on the lattice. It just linearly maps the lattice to C. And remembering that the lattice is the integer value part of the cohomology, we can think about the central charge as just some functional that takes in a homology and spits out a number. So it's going to be just some element in the cohomology group. That's all you need. And you can realize this by some closed form, by some closed differential form. And that's going to be the lambda SW that's hinting that we're going to call it the Seiberg-Witten form later. So for example, we can try to extract the coordinates from this geometric realization, from this notion of central charge, by choosing a basis of our homology group, so some basis of cycles. And then the coordinates are just going to be the periods of this Seiberg-Witten form. The integral over the two different cycles of the form give you your two different periods. And now let's impose the special Kähler condition. This fact that they're derived from each other by being the derivative of some function. Right, this sort of happened last time, but now I'm doing it in a more general case. So let's start with the period matrix, which is generally defined by normalizing these A cycles. So normalizing it so that these periods are all just 1, and then only looking at the other periods. Sorry, normalizing it so the A cycles all give just trivial, like the easiest periods possible, and all of the interesting stuff happens in the B cycles, but we can think about that as just dividing two matrices by each other if we want to. So it's just another way, we're just not doing this normalization ahead of time, but basically this gives us a form of the period matrix. Right, I should mention you're calculating the periods here, not of the Seiberg-Witten forms, but of the holomorphic forms. And there are, in this n-dimensional case, there's going to be n holomorphic forms to deal with. And from this special Kähler structure, we know that this period matrix has to be essentially the coefficients of our metric. It has to be realized as the derivatives of these two coordinates with respect to one another. And that's kind of hard. It's kind of hard to take derivatives. So instead, let's take just two numbers and divide those. So we can realize the derivative of one with respect to another by just dividing their derivatives with respect to some third variable, right? And then if we have this, we can just say, so this third variable is going to be just the coordinates on the base, just the original ones you started with, where your base is your Coulomb branch. And we can just look at these and we want them to be equal. And remembering that we have this formula for what AD has to be, it's just a period of this Seiberg-Witten form. We know that we know that the Seiberg-Witten form's derivatives have to give us the holomorphic things, right? So summing it up, we have two properties. First, the central charge is going to be the integral. The central charge acting on some element of the homology is just the period of the Seiberg-Witten form. What is the Seiberg-Witten form? It's defined by the relationship where its derivatives with respect to the directions on the base will give you all of the different holomorphic forms. So I find this kind of confusing. It's easy enough to work with. Like in the Seiberg-Witten case, they just had to do dimension 1 case where you don't have to deal with any of these indices, and then it's pretty simple to write down the Seiberg-Witten form from the formula for the holomorphic form. But when you have more than one holomorphic form, it's a little bit confusing. What does this really mean? So we can use a more coordinate invariant formulation of this, where we can think of this as saying that the Seiberg-Witten form will give us an isomorphism from tangent vectors on our base, on our moduli space, into the holomorphic part of the cohomology. And specifically, it's going to take a vector, and a vector that's a direction on your moduli space, and you're going to look at the covariant derivative of the Seiberg-Witten form with respect to that vector in the Gauss-Manin connection. And that is going to have to be these guys. They're going to have to be holomorphic forms, and it has to give you every holomorphic form from this construction. That's what needs to happen. So just for any, stepping back from cohomology, just looking at the Hodge structures, just any section of your vector bundle, you're going to have this map showing up where you take the vector and you look at the deformation of the form of your section in that direction on the base. And that will give you a map from your tangent space into the full cohomology, into the full Hodge structure. But specifically, we're going to get a Seiberg-Witten differential or an abstract Seiberg-Witten differential, specifically if the image of this is not just any subspace of the whole full cohomology, it has to be specifically the holomorphic subspace that we specified at the beginning. So this isomorphism is really at the heart of all of the structures. Like the Seiberg-Witten the Seiberg-Witten differential, in the original paper, it looks kind of like a computational trick, but really it plays a very essential role in the structure. So for example, it will give you your special Taylor structure by just taking some basis of homology and doing the same techniques we used to get coordinates before, just looking at the Seiberg-Witten form acting on these things abstractly. This will give us our special dual coordinates, and they're going to do everything you want them to do. But there's a better way to look at this. Because remember, we have this equivalence between weight 1 Hodge structures and between abelian varieties. And we're going to interpret the Seiberg-Witten curve in terms of these abelian varieties. So just to sketch out things so we can see what's going on here a little bit, we have our full Hodge bundle, this complex vector bundle that is over your whole moduli space. And we're going to have a half-dimensional subspace of that we're going to specify. It's going to vary holomorphically. It's a holomorphic subbundle. That's going to be like the 1, 0 part. And we also have an integer lattice. So we have this at every point in the base, except maybe at the singularities. And we get the abelian varieties by just kind of quotienting by the lattice, or in this transverse direction, quotienting this direction by the lattice. And that'll give you a bunch of tori. So there are two ways of looking at the same thing. Now, a bunch of tori, a bunch of abelian varieties. If you remember back from the first talk I gave all the way in the very beginning of the semester, it sounds kind of familiar, right? Because this fibration by abelian varieties is very close to the notion of an integrable system, or more concretely, with one extra thing, with one extra structure, this will be an integrable system. So we define some family of varieties, of abelian varieties, we define it to be an algebraically complete integrable system, or just integrable system, if there's some symplectic form such that the fibers, these abelian varieties, are going to be Lagrangian, which means that the symplectic form restricted to the tangent space of those fibers is going to be trivial. Right. And, you know, this integrable system structure, it's really nice. It gives you a lot of cool things, but in particular, it gives us an identification between the tangent space of the fibers and the cotangent space of the base. And this is basically given by, you know, how these are realized as integrable systems in the first place by a bunch of Hamiltonians, where you take the Hamiltonian vector fields and they just loop around in a very identifiable way. They just loop around these abelian varieties, right? And you have n commuting Hamiltonians, that gives you n commuting vector fields, and that gives you those sort of trace out your tori. But this, on the other hand, this says that basically the fact that this dimension is maximal, the fact that we have all the symmetries we can, that all n commuting Hamiltonians means that this identification is actually going to be an isomorphism. With all that said, what does the Seiberg-Witten differential do? Why do we care about it? We care about it because it exactly characterizes when a Hodge structure comes from an integrable system. This is the structure you need to turn some, you know, generic variation of Hodge structure. It could do anything you want. It could be from any family of abelian varieties, any nonsense, but it comes from specifically an integrable system if there is a Seiberg-Witten form. Right. So I'm not going to give a full proof, but I'm just to sort of summarize the idea is that this description I gave of the isomorphism between the cotangent bundle of the base and the tangent bundle of your fiber, that isomorphism really encoded the heart of all of the dynamics, right? Because that's what told you how to go from Hamiltonians on the base to their Hamiltonian vector fields, right? That is the essence of the phase space structure for an integrable system. So we can sort of, instead of looking for the whole symplectic form, we just have to look for this isomorphism. And if we have this isomorphism, then there are some arguments that say we can extend it. There's a unique symplectic form that comes from it, right? And this isomorphism, it looks extremely similar to the abstract way that we defined the variation of Hodge structure. Sorry, the abstract way which we just defined a Seiberg-Witten differential. Because the Seiberg-Witten differential gave us an isomorphism from not the cotangent space, but the tangent space of the base to the holomorphic parts of the fibers, the holomorphic subbundle of your Hodge structure. And all you need to do to switch between these two pictures is just take the dual, right? Because the tangent space of your abelian variety, thinking of your abelian variety as like this transverse direction here, the tangent space is naturally identified with the anti-holomorphic stuff. So the dual of the anti-holomorphic stuff, the cotangent space, that's going to be your holomorphic things. So the isomorphism that captures the idea of the Seiberg-Witten differential, the abstract Seiberg-Witten differential, is exactly what you need to equate the cotangent space of the base and a tangent space of the fiber. And you get a unique symplectic form. Yeah. We can also think about this a different way, like how did I get this formula up here? Because this is actually, you know, you're thinking of somehow we have to turn our abstract differential into a real differential form. And we can do that by geometrically realizing our variation of Hodge structure in a different way. You're not realizing it with the curves, you're realizing it with just this vibration of abelian tori. Secretly, we're using the polarization here to identify each torus with its dual. But basically, we're converting from a point on each torus. So we start with a point on each torus. That's the section defined by the Seiberg-Witten differential. And we're just using duality to convert that to a one form. And that gives us a one form on the whole space. And in fact, that one form, identifying the whole space with the cotangent, identifying the whole space with like the cotangent bundle of the base, it's actually the tautological one form. And this falls out almost immediately. So that was a little bit of a digression, I guess, because I mean, it's not really related to the rest of the BPS stuff and things we're talking about, but I thought this was really cool because you see these Seiberg-Witten curves and the question is like, what are they actually doing? What's special about them? Why do they keep showing up? And the answer is that they play this important distinguishing role in the theory of integrable systems. They tell you when your abelian varieties, your random family of abelian varieties is actually an integrable system. That's what they do. And in fact, let me see. Yeah, we can actually realize these. I mean, I've been talking about these differentials all this time. I didn't actually tell you what they were. There's a very canonical way to do it, which is to think about them as tautological one forms. Remember, we are characterizing our, let me scroll up. We're characterizing our curve as a spectral curve. It's sitting inside of a cotangent bundle. So why don't, and this cotangent bundle has a very natural tautological one form, which is basically just, y dx, like the sum of these guys, right? And its exterior derivative gives you the standard symplectic form on this cotangent bundle. But we can just pull back this tautological one form to the curve. And that gives us the Seiberg-Witten curve. And in particular, it's going to be meromorphic because that tautological one form, it has a pole all the way at infinity. In particular, it has a double pole. So the Seiberg-Witten curve form is just going to be some meromorphic form with the extra condition that every residue has to be 0, which means that it actually does indeed define an element of cohomology because, I mean, it doesn't matter which loop you take because the integrals of the loops around any given pole are going to be just a residue. They're going to be 0. So I'm going to forgo talking about why this is a abstract Seiberg-Witten differential in the sense I defined earlier, because I don't know. And I will make sure that nobody has any questions. Okay. So just to recuperate a little bit, yeah, so we have this understanding of what the geometry of Coulomb branches really is. It's this variation of Hodge structure. And we have this notion that the Seiberg-Witten curve in this variation of Hodge structure plays a very natural role. Now let's actually talk about some BPS states, right? Let's use this, play around with this a little bit. So I'm trying to decide how much of this I want to talk about. Okay. We can actually think of BPS states as geodesics. I think this is kind of cool. It's a very unique it's an application of this Seiberg-Witten curve formalism that is extremely useful in actually telling you how to find BPS states. It's not something you can do normally, but with this geodesic picture, it's something you can do. So basically, remember that central charge we defined? It's just the periods of the Seiberg-Witten form. Well, the whole point of BPS states is they satisfy this BPS bound, that the energy, the mass of any state has to be, it's in general true that the mass of any state is bounded below by these periods. So a state who whose charge lives in this homology class has to have mass above this amount. And when that bound is saturated, it's called BPS, and these are actually equal. But we can do just a little trick of rewriting this and writing that this, taking the norm squared of this period integral, and just by doing Cauchy-Riemann, we know that this has to be less than the integral of the square of the interior. And now suddenly, it's not a period integral, this is a metric. It's a metric defined by a quadratic differential from squaring the Seiberg-Witten form. And what we're doing is we're just integrating the length of this path in this metric, right? So it's the same thing, right? Just said a different way, I guess. And BPS masses are when the mass actually saturates this bound and you have minimal mass possible. And remember, mass is length. So these are just geodesics, right? They're minimal length paths. Yeah, so we can calculate BPS masses with this trick because we're relating BPS masses to the lengths of these geodesics. And in fact, it's just important to note that these metrics are going to be flat. That's the really cool thing about these. That's in general what these sort of metrics do. They give you flat metrics on the surface, but there are some like zeros and poles, so it's interesting to study these. Right. So this sort of brings up a sort of schematic picture of what's kind of going on, because all we set up here is that we can calculate the masses with geodesics. But what if we pretend, and then these paths were just kind of incidental. What if we pretended that those paths were actually, the real states? Those paths were the real states, and following through all of the analogies, we're thinking of the charge of these things as the first homology, right? And I just said that the mass is like length. So the BPS states, they're going to be minimum length states, pull them taut. And these are going to be geodesics. So,
but they have to lie in a leaf of the foliation, right? So that there's this constant phase condition.
Yeah, so the way that constant phase condition comes up is right here from this Cauchy-Schwarz. You actually get equality in this when the Seiberg-Witten curve is always constant phase. That will give you equality. So when it is constant phase, we can specify the phase ahead of time if we want to. And that's equivalent to, as you said, that's equivalent to defining a foliation, where we're not looking at all the geodesics, just a specific line, a specific collection of them that are all parallel roughly. But in general, when we're counting BPS states, we're not making the constant phase condition. And we'll also comment that the way constant phase comes up in Guyton-Moore-Knightsky is because, I believe it's because they're actually coupling these BPS states with, strings at the origin, right? These framed BPS states, and that gives extra structure. And I think that's what enforces this phase. But in my perspective, we're not doing any of that. So we don't have to worry about it. For people who are familiar with Guyton-Moore-Knightsky. And this essentially the idea is that we can count BPS states by counting geodesics, and that's cool. That's a fun thing to do. Okay, so I talked a whole lot about these Seiberg-Witten curves, but I said at the very beginning, remember the title of this talk, unified picture of BPS states. What am I unifying? Just a second. Okay. I'm sorry. Things got tangled up. Anyway, there's another perspective on this using string theory. It's sort of a question of what do these Seiberg-Witten curves mean? They're not just a computational trick. They do have real physical meaning. And it comes from string theory interpretations. So instead of going into all of the stuff about what the string theory is, let me just tell you the sort of correspondence that plays. We're going to go from these Seiberg-Witten curves to these string theory objects. Right? And in particular, this is the process of geometric engineering, which I think is it's a really cool name to call something. But basically, it's choosing a Calabi-Yau freefold that you want to compactify under that gives the right properties. So we're just going to pick a really simple one. Just take, the complex plane in like the algebraic geometry sense, where it's a two complex dimensional vector space, and just mod out by Z2. That swaps. It negates things, right? And if you do that, you're going to get a cone. That's sort of what this structure is indicating. You're going to get a cone point at the origin. But you can resolve these singular points and turn them into whole spheres. So now it's something which isn't quite a sphere, but like it's not quite a cone. It's like this sort of hyperboloid picture. And so these are resolutions of our ALE fibers, I guess. And we can characterize sort of the size of these exceptional things, the size of all of these spheres, which map down to the cone when you pull it back to the singular part. That's like our parameter, right?
You said threefold, but is C2 mod Z2 just a two-dimensional substitute, or yeah?
Sorry, so this is a two-dimensional complex manifold. I have not described the Calabi-Yau yet.
Okay.
It is because you have a bunch of these copies of these two-dimensional complex manifold fibering over some base curve.
Okay.
That's where you get 3 dimensions, right? So in particular, we're going to take the base curve to be just like the base of our, what is the base curve? The base curve is like, the P1 that we're double covering, right? So the Seiberg-Witten curve is a double cover, but we can think about it a different way as these copies of these spaces where the spheres are going to be, we're tracking the spheres. And we're going to arrange the spheres such that like their top and bottom correspond with the top and bottom of the Seiberg-Witten curve. So, I mean, I'm saying a lot of words, but like it's a very simple equation that describes this process. So 4 variables yields a 3-dimensional space. And it's going to have the property that at the branch points, where the Seiberg-Witten curve smashes to the distance between these two layers smashes to 0, that's going to be the cone points. So just to summarize a little bit, take the high-level overview, is that we have a very similar picture here, where string theory gives us a lot of rules about what these states represent. And like, we have this charges. Charges come from like the H2,1 cohomology groups and stuff like that. But really, it all fits in exactly the same framework that I described earlier, right? Where we have a Hodge structure where we're looking at specifically the third. In this case, it's going to be the middle homology. That's the stuff where interesting things happen, like these spheres collapsing to 0. We're looking specifically at that space, and we have a Hodge structure on that, which we're going to think of as level 2. It's going to give us what we call the intermediate Jacobian. And in some cases, this actually gives us an integrable system, Calabi-Yau integrable system. So again, same song and dance. We can find an analog of the Seiberg-Witten form. In this case, it's going to be really nice. It's just going to be the unique holomorphic free form on our Calabi-Yau. And it tells us that, remember, the BPS states on the Seiberg-Witten curves, those were geodesics. They were the length minimizing, the energy minimizing representatives of their homology class. And in here, we get the same thing, where the BPS states correspond to essentially these free spheres, which is a two sphere that's like sitting above each geodesic, where it collapses to zero at the endpoints, at the branch points. And that free sphere, I mean, it's going to give you a class in homology, and that class is going to have a mass, which is the period. And it's going to be minimal when it's what's called a special Lagrangian, I think, a special Lagrangian submanifold. So we have the same thing popping up again, right? This notion of BPS states as some energy minimizing representative of a cohomology class that fits into this framework of variations of Hodge structure. Now, my question is, this is what I wanted to answer when giving this, I didn't get close, but my question is, the question is, how far can we push this? Because remember, BPS monopoles, those saturate an energy bound too. They saturate the like the Yang-Mills energy. And so can we think about these in terms of these BPS states? And these BPS monopoles, they come up in supersymmetric, they come up in the limits where you have the masses of these BPS states vanishing. And when that happens, that's where all of the like Seiberg-Witten invariance and stuff comes in, because you have to integrate over the moduli space of these monopoles. But in the semi-classical perspective, we can represent BPS states in this regime as essentially essentially a supersymmetric quantum mechanics problem, where the states correspond to, classically they just move like geodesics on this moduli space of manifolds. It's a slowly varying monopole, but quantum mechanically, this becomes harmonic functions. And suddenly your BPS states are classified by, again, a cohomology, right? And these same cohomologies that come up here. And it's really interesting because, for example, this monopole space, it has all of these, it has an integrable structure too. So like, I don't know, maybe that integrable structure hiding in this monopole space is secretly the same integrable structure as what you get from BPS states, thinking about them as variations of Hodge structure. There's all of these different things that come together and under the umbrella of BPS states. And the naive hope is that they're all actually the same. But I can't prove that. And I guess that is all I have to say today. So thank you for having me. I guess I did have a question for the experienced people in the audience, which was that, I'm trying to like fit everything to this big square hole of variations of Hodge structure. But basically, the only times BPS states came about is in the dimension 1 case with these Seiberg-Witten curves, and in the dimension 3 case with these Calabi-Yau free folds. So what I'm wondering is like, why are the only, it seems like those are the only things that come up in physics. Like nobody talks about a Calabi-Yau tenfold, And I guess it makes sense because like, you know, you can't, string theory anomalies or something like that. You can't define string theory with that. But mathematically, like what's special about 1 and 3? That means that you get all of these structures like Calabi-Yau integrable systems and Hitchin systems and stuff like that. Like is 3 special in some way?
Well, perhaps, but there's plenty of literature in the physics literature also about Calabi-Yau two-folds, which are K3 surfaces, and Calabi-Yau four-folds also. So I'm not sure that 1 and 3 are the only possibilities. They're sort of the most obvious ones, but maybe not the only possibilities.
Well, I guess specifically from an integrable systems perspective, on curves, you get these Hitchin systems. They come up all the time. And you have these Calabi-Yau integrable systems, which is basically coming from this Hodge structure I described here. But those are Calabi-Yau 3-folds. Like, is there like a Calabi-Yau 5-fold integrable system or like a 10-fold one or something? It's the rhetorical question, I guess, because there's a lot of
algebraic geometers here answer that. I mean, I think in general, algebraic geometry gets more and more complicated the bigger the dimension gets. So, you know, it's natural to start with dimension 1. Dimension 3 is sort of an obvious choice because string theory basically lives in 10 dimensions. And if you subtract off 4 for Minkowski space, you know, because you want this sort of to translate to usual general relativity, et cetera, that leaves you 6 real dimensions or 3 complex dimensions to work with. So there's sort of natural reason for looking at Calabi-Yau 3-folds. I don't know.
Yeah, as you mentioned, there are also Calabi-Yau 2-folds. So the K3 surfaces, they do also appear because compactifying string theory on that K3 will give you a 6-dimensional theory, which is interesting for studying to sort of learn some more of the tricks and tools of the trade. You can also consider compactifying on a Calabi-Yau 4-fold. That's most typically done with the F theory. And the Calabi-Yau 4-fold ought to be elliptically fibered for that particular purpose. But in principle, you could extend that higher. It's not going to be terribly interesting for physics because, well, string theory is limited by a total of 10 real dimensions, at least one of which has to be time-like, so that's a Lorentzian structure. And so if you cut down what's called the light cone, 1 time and 1 space-like coordinate, you're left with 8 real coordinates. So there is not much more room than a Calabi-Yau 4-fold there. Unless we figure out how to do a Calabi-Yau 5-fold, where you take, so that would be a Euclidean space, but then you somehow do what physicists refer to as a Wick rotation. So an analytic continuation of one of the coordinates into a time-like coordinate. Paul and I have written a very long time ago about some such fantasy, but that's the physics interest. But in general, you know, as Jonathan was saying, from a point of view of an algebraic geometer, who cares? You can consider a Calabi-Yau 17-fold if you like.
Except that the algebraic geometry gets more and more complicated as the dimension goes up. So, you know, since 3-folds are complicated enough from the point of view of algebraic geometry, people haven't really studied very much beyond that.
Right.
Interesting, thank you.
All right, should we stop the recording?